We'll continue ahead with heat and thermodynamics. We were discussing about thermal expansion last time. So a couple of things in that we'll continue ahead and then move on to the next section, which will be calorimetry. So we had seen about coefficient of linear expansion, coefficient of surface expansion, and coefficient of volume expansion, and the formulae related to that. Now, today we'll begin by understanding how density varies with temperature. So variation of density of a material with temperature. So we know that density, say D, is equal to mass per unit volume. Or we can write the density of an isotropic material having uniform density as m by v. So we know volume varies with temperature according to this relation. Okay. Or delta v by v is equal to gamma delta t. Therefore, if at temperature T naught, D is equal to D naught. Okay. Where m is mass, v is volume. At temperature T equal to T naught plus delta T. So this will become like this. Okay. So if we compare this relation now with this relation, you can understand how density varies with temperature. So comparing the equations 1 and 2, you can see that density at temperature D T is equal to density at temperature T naught divided by 1 plus gamma delta T, or power minus 1. Okay. Now we can use that binomial approximation method. So 1 plus x to the power minus 1 can be approximated as 1 minus x if x is very small compared to 1. This is called binomial approximation. So 1 plus gamma delta t to the power minus 1 can be approximated as 1 minus gamma delta t, because gamma delta t is very small compared to 1. Okay. So therefore the next step here becomes this. So this becomes a variation of density with respect to temperature. So just make a note of this quickly, then we'll discuss some application examples. Okay, so hope this derivation is clear. So let's understand a quick example. So a solid metallic sphere has coefficient of linear expansion equal to 6 into 10 raised power minus 5 per degree C. Okay. And undergoes a temperature rise of delta T equal to 40 degrees C. Find the percentage change in the sphere's radius r and diameter d. Then second, surface area s. S has the formula 4 pi r square for a sphere. Volume v. V has a formula 4 by 3 pi r cube. And finally, density d, mass upon volume. Okay. So it's a solid metallic sphere made of metal which has coefficient of linear expansion alpha so much. Okay. So from that data, we have to calculate these things. Just try out this question quickly. Yeah, so anybody worked out the question, please send me the answers. Okay, let's understand the solution to this question. So what is happening here, see, is that when we talk about a spherical body, its radius and its length, radius and diameter, these are what we call linear dimensions. So the diameter of the sphere, which is twice the radius, diameter d and radius are linear dimensions. Okay, so their behavior with temperature will be like this. Okay, so r at some temperature t will be r at temperature t naught into 1 plus alpha delta t. Diameter at some temperature t will be diameter at temperature t naught into 1 plus alpha into delta t, where you can see this ratio exists, and delta t is t minus t naught, the temperature difference. Okay, so the percentage change will be just alpha delta t converted into a percentage. So alpha is 6 into 10 raised to power minus 5. The temperature change we are seeing is 40. We have to just convert this into a percentage. So this is 2.4 into 10 raised to power minus 3. So 0.24% increase. The radius will increase by a 0.24% increase. Okay, now likewise the diameter will also change by the same amount. No, but the percentage change will not be the same return. You understanding, Prince? See, the percentage change will be the same. The change in diameter will be double of the change in radius. That's correct. Okay, if diameter is equal to 2 times radius, so the change in diameter will be 2 times the change in radius. But change in diameter divided by diameter is the same as change in radius divided by radius, which is alpha delta. Therefore, the percentage change in the diameter is the same as the percentage change in the radius, which is 0.24%, and it increases by that. Yeah, I'll explain it, but first make sure you understand this point, that because the diameter is just double of the radius, so if the radius undergoes a 0.24% increase, the diameter will also undergo a 0.24% increase. So it's like, if your original radius was 100 centimeters, suppose, so your new radius will become 100.24. So your original diameter would have been 200. So your new diameter will become 200.48. So this is also a 0.24% increase. This is also a 0.24% increase. Understood, my Prince? Okay. So just write this down. So this is the A part, the percentage change in the radius, and this is now the B part, the percentage change in the diameter, and they're both equal to 0.24%. Now C part, you have to calculate the percentage change in the surface area. Okay, so anybody got the percentage change for the surface area? It's very simple really. We'll just use the formula beta into delta T. Yes, very good. That's correct. No, okay, correct. 0.48, Ganesh. Okay. So surface area S, that will behave such that delta S by S is beta into delta T, or twice of alpha into delta T, because beta is equal to twice alpha. Or we can also understand that surface area is proportional to square of radius. So the fractional change in surface area will be 2 times the fractional change in radius. So there are two ways of understanding this. Okay. So beta is going to be, how much was alpha now? 6, no? So 1.2 into 10 raised power minus 4, and delta T was 40 degrees C. So beta delta T will become 4.8 into 10 raised power minus 3. So fractional change is that much. So percentage change will be, okay, 0.48%. So surface area increases by 0.48%, just as radius and diameter increase by 0.24%. Yes, that's correct, Kanishk. Very good. So the volume will increase according to gamma delta T, or okay. So similarly, when it comes to the volume, we can use this, or we can use the fact that volume is proportional to R cube. Therefore, fractional change in volume is 3 times fractional change in radius, or percentage change is 3 times. Okay. So it should be 0.72%. Okay. So same way. So gamma is, no, it's not square beta. The surface area is proportional to square of radius. That's why the fractional change is 2 times the fractional change in radius. That is the principle of error propagation, which you've also learned in units, dimensions, and measurements. Okay. The relation is like this, that if y is proportional to x to the power n, then delta y by y is n times delta x by x. This is the relation, keep in mind. In fact, this is why beta is equal to twice of alpha and gamma is equal to 3 times alpha. This is a precise reason why this happens. Okay. So now coming back to this question, the volume expands by 0.72% for a temperature rise of 40 degrees. So that will mean that the density will decrease. If the volume is expanded, so the density will decrease by 0.72%. Yeah, Prince, you've written this down, no? Up to surface you must have written down, no? So write down for the volume now. Achha, surface is remaining, okay. I'll just Yeah, Prince, I'm explaining that. Okay. So see, this I was explaining because somebody had asked me how we get this result, that if surface area is proportional to r square, then why delta s by s is equal to 2 times delta r by r? How we get this result? So that comes from this general formula. Okay. This part, this is a general formula for propagation of error. Okay. Another example of this you'll remember was time period of pendulum is proportional to square root of length. So that's why the percentage of fractional change in time period was half of delta L by L. We had done this last time to do with time period of pendulum. Any quantity, beta, y and x are any two quantities, any two physical quantities. If they are related by a, that's why I said it's a general formula. ये आपने measurement वाले chapter में पढ़ा है ये, है ना? Okay. So for example, if we take y and x as radius and surface area, we get this relation here. If we take it as time period and length of the pendulum, we get this relation here. So any two quantities which are related by some power like this is the principle that applies to the percentage change or the fractional change. Okay. So now from that, we also understand this part, that this last part, the relation between volume and density. Okay. So density is inversely proportional to volume. No? So therefore, if the volume expands by 0.72%, it implies that the density will decrease by 0.72%. So delta D by D will be minus 0.72%. Because remember, we had the relation that density decreases with temperature increase. 1 minus gamma delta T. So delta of density by density, fractional change was minus gamma delta T. So from this, we are getting this. Okay, now the final part we quickly discuss here about thermal expansion is the behavior of a cavity in a material with temperature change. If there's a gap or a cavity in a material, how it behaves. So for example, suppose we have this kind of situation. We have a solid block which has a spherical cavity. So a solid metallic block which has dimensions okay, with a spherical cavity or hole of radius r naught at t equal to t naught. So what will happen here is that at a temperature T naught plus delta T, where alpha is coefficient of linear expansion of the metal. But the cavity, can you guess what happens to the cavity? Will the cavity expand or will it contract? When I increase the temperature, it's obvious that the outer dimensions, length, width, and height, and all should increase according to this formula. Okay, alpha delta T. Delta L by L is equal to alpha delta T. But what about the spherical cavity? Should it expand or should it compress? Yes, very good, Tantrish. That's correct. Cavity also expands, okay, such that the radius of the cavity it behaves according to okay, the volume of the cavity. It behaves according to so the important thing here is that the cavity will expand in the same way as the material we have removed to create the cavity. So what will happen here is the cavity, which in this case is a spherical cavity, will expand on heating just like the material removed, that is a solid metal sphere, to cut the cavity. To create the cavity or cut out that portion, we have removed a solid sphere of metal. So just like that solid sphere would have expanded according to these formulae, the cavity, the empty portion is also going to expand in the same way. In other words, if I were to fit that solid sphere again over here, that solid sphere would have expanded in such a way that the cavity exactly fits with the solid sphere. So that's why the cavity has to expand in such a way to accommodate, the solid sphere which we have removed. So the cavity will expand in exactly the same way. Its dimensions will expand in exactly the same way as the dimensions of the solid sphere which was removed to cut out the cavity. So this is an important principle you have to keep in mind. Make a note of this, please. Okay, so now a very important consequence of this concept here is that the capacity of a vessel B. For example, we have a glass container. We have an open glass container. Okay. So if the capacity, which is the volume of its inner empty space, okay, that capacity is V, then delta V by V will be equal to gamma delta T, or volume at temperature T will be volume at temperature T naught, where gamma is the material, I mean coefficient of volume expansion, of the material. In this example, glass of the container. So the capacity of an empty container, it also expands according to the same formula for volume expansion. So in other words, an empty container will expand in the same way as a solid container made of the same material, or a solid block made of the same material. So an empty open glass cylindrical container will expand in the same way like a solid cylinder of glass of the same dimensions. Hence, the capacity of that cylindrical container will increase according to the same formula as the volume increase for a solid cylinder of glass. Yes, Prince, that's correct. So gamma is equal to 3 times alpha for that given material. Okay. So now from this, we'll see another aspect of this, and that is the apparent expansion of a fluid in a container. So why we say apparent expansion? Because the fluid expands with temperature increase, but the container also expands. So the volume of the fluid that we measure using the given container will not be accurate because the container itself has expanded. Okay, so let's understand this. So a glass container, okay, used to measure volume, okay, is calibrated, okay, or you can say it is graduated. When you have a container which has markings on the side like this, we call it a graduated container. So a graduated glass vessel or container, something that is used to measure the volume of fluid inside it. So we have this type of graduations. Okay. So this is to measure volume, let's say in milliliters. So this one is calibrated at a temperature of 5 degrees. Okay. And a liquid measures up to a volume of, let's say, 200 milliliter. In the container. So we place some kind of liquid in the container. And at 5 degrees C, the liquid volume reads 200 milliliters. Okay. Now, the alpha of glass is 2 into 10 raised power minus 5 per degree C, suppose. And the coefficient of volume expansion of the fluid or the liquid that we have inside the container, that is 4 into 10 raised power minus 4 per degree C. So if the system, that is the container plus the fluid, is heated to 55 degrees C, okay, find the true volume of fluid, the true volume of liquid at 55 degrees C. The measured value at 55 degrees C and the percentage error in the measurement. Why there's a percentage error? Because the container has expanded. So it's not going to measure volume accurately because it was no, this is an example. We are doing a numerical example. The concept we are using, Prince, is thermal expansion, which we discussed earlier. So this is a numerical example. Yeah, so what will happen here is that the calibration of the container, the graduated container, is done at 5 degrees C. So because the container is expanded when we raise the temperature to 55 degrees C, is going to measure inaccurate volume. Okay, it will measure less than the true volume of the liquid because the container itself has expanded. So that's why there's a difference between the actual volume of liquid that will be there in the container versus what we are able to read. The reading of volume that we are getting using the graduated container, there'll be a difference between that and the actual volume. Hence the concept of percentage error. Yeah, that's okay. I understood better. But just try out this question now. So just try out this question. We'll discuss. Okay, so anybody worked out this question, please let me know. Okay, so first of all, let's understand the actual volume of the liquid. So for the A part, we'll just use the fact that the true volume of the fluid, let's say that is Vt. This is the gamma of the liquid into delta T. So the true volume at 55 will be the volume at 5 into 1 plus, now gamma of the liquid we have taken as 4 into 10 raised power minus 4, and the temperature change is 50. Okay. So this actual volume was 200 milliliters, and this will become 2 into 10 raised power minus 2. So correct, that will become 204 milliliters. So the volume of the liquid, it expands by 2%, you can say. Okay. Whereas the measured value of volume, how much that will become. So to understand that, now see what is happening. For the container, okay, the least count, okay, that is the volume of one division, that was equal to 1 milliliter at a temperature of 5 degrees C. But the least count at 55 degrees C, that will become 1 milliliter into 1 plus gamma of glass into delta T. Okay. Now alpha of glass was given to us as 4 into 10 raised power, what was it? Sorry, 2 into 10 raised power minus 5. Okay. So this will become the least count, or one division will become 6 into 10 raised power minus 5 into 50. This will become one division. So the measured volume will be the true volume divided by the least count. Okay. So the true volume is 204 milliliters, but the least count is this. So that's why you can see that the measured value is going to be less than the true value, and we can write this as 204 into 1 plus 0.003 to the power minus 1. So we can approximate this as 204 into 1 minus 0.003. So that is 204 minus 0.612. Right. So this becomes so this is the measured volume. Let's say V prime is the measured volume. See what is happening, Prince, that because the container is expanding now, so its least count. What is the least count of a measuring device? It's the smallest division. It's the value of one division on the scale of the device. So the least count will expand from 1 milliliter of volume into 1 milliliter into 1 plus gamma delta T for glass. Because remember, the glass is expanding in this, the volume of the container is expanding in the same way like glass expands because it's made of glass. So got it now? So the least count of the container, which was accurate at 5 degrees C because it was calibrated at that point of time. So it was 1 milliliter at 5 degrees C, but at the new temperature of 55 degrees C, the least count of the container at this new temperature, the least count has become incorrect. It has an error in it because the container is expanded. So it has a wrong value of 1 milliliter into this factor. That's why it's going to measure less than the true value of volume. Yes, gamma is simply 3 times alpha. So that will substitute here. Okay. So just like, we had done a problem with a scale earlier. So the divisions on the scale would expand with the temperature increasing. So at a higher temperature than the calibration temperature, the scale would read the wrong value of length. So like that, at a higher temperature than the calibration temperature, this graduated vessel of glass used to measure the volume is also going to read the wrong value of volume because it has expanded. A part of the question we did, number one. The true volume we found out. Actually, you've not written this down. Okay, write this down quickly. Okay, done now. Yeah, so the B part only. Okay, so now you can see that the true volume was 204 milliliters, whereas the measured value, therefore percentage error, the negative value of error means that the value measured is less than the true value. So this basically now means that the measurement is lower than actual value by 0.3%. So this kind of combines the concept of errors from errors and measurements with this concept of thermal expansion. So this is the type of question you can expect at the JEE level, because it's not going to be only formula based question. So from thermal expansion, you don't expect a question which is just direct application of the formula, but along with that formula, some other concept is also being used. Like over here, the concept of error propagation and percentage error in measurement is being used. Okay, Andresh, I will solve that question also. We'll keep some time aside for discussion of HC Verma questions. During that, I'll solve that. Okay. But what I want to do with the remaining bit of time that we have today, Achha, Prince, you have to still write down. Okay. Yeah, because the measurement is less than the true value. No? So I've written in the end, it is lower than the true value. You can see V prime is less than V. That's why the error is a negative error. Okay. Yeah, so Tandrish, I will keep some time aside in the next lecture also for discussion of problems from H.C. Verma from heat and temperature, which is this chapter. But today, in the remaining time, I also want to start with the next section, which is calorimetry. It's a very easy section, so that in the next lecture, we can wind up both these things, thermal expansion and calorimetry. So the term calorimetry comes from the unit of heat called calorie, which is a non-SI unit. No, only part of it, but I'll just explain. But you can get started on this chapter. So this is a familiar thing for you from 9th, 10th. Okay. The next lecture, we'll pick up the questions and all from both these chapters. Okay. So calorimetry is to do with the heat exchange and temperature change, okay, or state change for a given material. How the heat exchange of that material with its surrounding environment affects the temperature or affects its state. Okay. So we can understand this very easily by just understanding an experimental graph that we can plot when we look at the behavior of a given body or given material in terms of its temperature and the amount of heat supplied. So if Q is the amount of heat supplied and T is the temperature of the body or the material, and temperature can be in any unit including Kelvin or degree C or whatever, Q is the heat supplied to the material, okay, in joules or calories or whatever. Okay. Then the experimental analysis we do for any material will show us a behavior which is like this, that generally the temperature will increase linearly with respect to heat supplied, but up to a certain point. And then what happens is that there's a state change that occurs. So while the state change is occurring, for example, if we are heating ice from a temperature of sub-zero, then the ice will first heat up to 0 degrees C. But the moment it reaches 0 degrees C, the temperature will not change till melting is completed. And then again, the temperature will start to change because we have water till we reach the boiling point. And the moment we reach 100 degrees C or the boiling point, again, heat supplied will result in vaporization or boiling and no temperature change till all the water is converted to vapor. And then that vapor will again increase in temperature. So the behavior of temperature versus heat supplied has this kind of a nature, that if originally a material was in solid state, if the state of the material was solid, then the temperature increases with heat supplied proportionately till we reach a certain temperature called the melting point. Now at the melting point, what happens is heat supplied does not result in temperature changing, it results in melting. So that is a state change. Melting is a state change from solid to liquid, as you know. Then once all the solid is converted to liquid, again the temperature starts to rise as we supply heat till we reach another specific temperature called the boiling point, okay, where boiling starts occurring, which is a state change from liquid state to vapor state. And once the vaporization or boiling is completed, then the vapor or gaseous state again behaves in such a way that the temperature rises proportional to the temperature change, to the heat supply. Okay. Just make a note of the graph, and then we'll look at the interpretation of the graph, and we'll look at a couple of quantities like specific heat capacity and latent heat of vaporization, latent heat of fusion, etc. Yeah, this is a new next chapter in H.C. Verma, or your module for that matter. It's a very short topic. The next one after this will be yeah, it will come now. Yeah, it got disconnected. That's why. Okay, so this is the behavior of the temperature of a given material with respect to heat exchange. Yeah, I was just saying that calorimetry is the second chapter after thermal expansion in both H.C. Verma as well as the module. And the next chapter after that will be kinetic theory of gases. Calorimetry is a very short chapter, just a couple of definitions in it, very easy also, but then it does not have too much weightage in the exams also. Okay. So for a given material at a temperature less than the melting point. Okay, the state will be solid. Okay, and temperature change will be directly proportional to heat supplied. Temperature rise is directly proportional to heat supplied. As long as we are talking about a temperature less than the melting point. As long as we are talking about temperature less than melting point. So that's why the graph is a straight line in the first section. For the temperature less than melting point, you can see the relationship between temperature and heat supplied Q. It's a straight line graph. That means there is direct proportionality. Okay. So that means that temperature change or the heat supplied is some constant multiplied by temperature change. So that constant, as you know, is called the heat capacity. Okay. So Q is equal to C into delta T, where C is called the heat capacity, and further the heat capacity is the mass multiplied by specific heat capacity. So we have the formula Q is equal to ms delta T. This is a formula that you're familiar with from before. S is called specific heat capacity of the material. In this case, it's in solid state because the temperature is less than the melting point. So this specific heat capacity, it is measured in joules per kg per Kelvin, or joules per gram degree C, or calories per gram degree C. Yeah, I'm coming to C. C is called the heat capacity. Heat capacity is It is heat supplied per degree change in temperature. Therefore, heat capacity is measured in joules per Kelvin or calories per degree C, etc. Whereas specific heat capacity is Q upon M delta T. So specific heat capacity, that is the heat supplied per unit mass per degree change in temperature. And that's why we just saw that it's measured in joules per kilogram Kelvin or calories per gram degree C. So that is the difference between specific heat capacity and heat capacity. A heat capacity is for a given body or a given material, but specific heat capacity is for the unit mass of that material, for 1 kg or 1 gram, depending on the unit. I hope it is clear the difference between specific heat capacity and heat capacity. Okay. Now the next thing, state change. For example, melting, which is solid to liquid, okay, or boiling, which is liquid to vapor. Now this state change occurs at a particular temperature, which is the melting point or boiling point for the given material or substance. And during state change, there is no temperature change that occurs with heat supplied. Only state change occurs. And the heat supplied is related to the mass of material undergoing state change by something called latent heat. It's a specific heat capacity. I've just given the definition of it. Is it clear now, friends? Okay. So now the next thing, during state change, when the temperature reaches the value of melting point of a solid or the temperature of a liquid reaches the boiling point, then the heat supply does not result in temperature change. It results in state change until the complete state change has occurred. So when you have the solid at melting point, any heat supplied will result in melting and no temperature change will occur until all of the mass of solid has liquefied or has melted. Once the melting is completed, if we further supply heat, only then the temperature will rise further. Okay. So M is the mass of material undergoing state change. That is the mass of solid melted or mass of liquid vaporized. Okay. So Q is the heat needed to state change or change the state of M mass. And the quantity capital L is called latent heat, okay, of fusion or of vaporization. For solid to liquid, or liquid to vapor. Okay. So L is equal to Q by M. So latent heat is the heat needed Yeah, so layman terms, the heat supplied per unit mass. Okay, so heat supplied for state change per unit mass. So that is why latent heat is measured in joules per kg or calories per gram. Okay. So these are the two formulae that we use in calorimetry. And in the next lecture, we will see the type of numerical applications we have for these formulae. And we'll also look at some more numerical examples from thermal expansion, including questions from the HC Verma set. Okay. So we'll complete all that in the next lecture. And then after that, we will continue ahead with kinetic theory of gases, from where the, the main bulk of the heat and thermodynamics part comes, which has more number of questions coming in JEE. So more weightage. So that part starts from kinetic theory of gases, but obviously you've done part of kinetic theory of gases in chemistry also. So it will be easier for you to understand this section. Okay. So that's it for today's session, people. Wish you all the best.